Hello, my dear students. Today we are going to discuss the topic called collision. We already learned that in collision, physical contact may or may not be there. And we defined collision as the process in which there is a large impulsive force involved and energy and momentum of the interacting particle change. Alright? The next important point we learned was the total energy is conserved in every collision. Correct? The total energy is conserved in every collision. And we classified collision into three types. Do you remember? Yes. There was elastic collision, we had inelastic collision, and the third category was perfectly inelastic collision. Correct? Perfectly inelastic collision. Perfectly inelastic collision. And what is the difference between these three types of collision? In elastic collision, both momentum and kinetic energy are conserved. Alright? Both momentum and kinetic energy are conserved. Whereas in inelastic collision, we have only momentum conserved. Okay, so kinetic energy will not be conserved. And perfectly inelastic collision also, we have only momentum conserved. Alright? But what is the basic difference between inelastic collision as well as perfectly inelastic collision? The difference is that in perfectly inelastic collision, the colliding bodies will stick together after the collision. Alright? So before the collision, it will be two independent bodies, but after collision, the two body will stick together. So we can tell like colliding bodies stick together after collision. Alright? Colliding bodies stick together after collision. And there is maximum kinetic energy lost in perfectly inelastic collision, right? Maximum kinetic energy is lost where it is in perfectly inelastic collision. So you will be remembering these points that we have already studied. Alright? Now, coming into more detail about elastic collision, okay, my idea is to just remind you those things we learned in the classroom. Okay, in elastic collision, yes, we told that both momentum as well as kinetic energy is conserved. So we have two types. First of all, what is head-on collision? Yes, head-on collision have another name like one-dimensional collision. Alright? And what did you study in it? Yes, before the collision and after the collision, the bodies will be moving in the same line. Correct? So two bodies are there. M1 moving with the initial velocity U1. There is another body M2 moving with initial velocity U2. Okay. Both are moving in the same line. Both are moving in the same line. As you can see here. Okay, both are moving in the same line. So this is before collision. Okay, before collision. Under what condition these two bodies will collide? Yes, the initial velocity of the first body have to be greater than the initial velocity of the second body. Then only the M1 mass will collide with the M2 mass. Alright? So before collision this is the situation, and after collision what is the situation? Yes, m1 will have a velocity, final velocity v1, m2 will have a final velocity say v2, correct? So that is the situation after collision. And you can clearly see here, before collision as well as after collision, the bodies are moving in the same line, alright? Therefore, this is head-on collision or one-dimensional collision. Now, about elastic collision, we told momentum is conserved, right? Momentum is conserved. What do you mean by conserved? Yes, momentum of the system before collision as well as after collision have to be the same. Momentum initial should be equal to momentum final, which means that momentum initial means, yes, m1 u1 plus, what about the momentum of the second body initial, m2 u2 should be equal to m1 v1 plus m2 v2. Okay, it's a very important equation. The next one we told was kinetic energy is also conserved, alright? Kinetic energy is also conserved. So kinetic energy conserved means kinetic energy initial is equal to kinetic energy final, alright? So we can write like half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square, that is the kinetic energy of the final kinetic energy of the first body, right? Plus, what is the final kinetic energy of the second body? Yes, half m2 v2 square. So kinetic energy of the system before collision is equal to kinetic energy of the system after collision, alright? And from 1 and 2, on solving 1 and 2, on solving 1 and 2, we will get an equation, right? What is that equation? Yes, which was very important. u1 minus u2 is equal to v2 minus v1. Do you remember? Yes, this we done in the class. What is u1 minus u2? That is velocity of approach, alright? u1 minus u2 and this part is velocity of approach, okay, velocity of approach. And what is this part? It is velocity of separation, velocity of separation. Alright, so from this derivation we can obtain the final velocity of the colliding bodies, right? So the equation for final velocity v1 is m1 minus m2 by m1 plus m2 into u1 plus 2m2 u2 by m1 plus m2. I hope you guys are remembering this, right? What is the final velocity of the second body? Yes, m2 minus m1 by m1 plus m2 into u2 plus 2m1 u1 divided by m1 plus m2. Okay, so these are the equation for the final velocity v1 and v2. Okay, now here we have learned many special cases. I hope you guys will be remembering those special cases. Alright, we have learned many special cases. What was our case 1? Yes, the case 1 was, suppose the m1 mass is very greater than the m2 mass, right? m1 mass is very greater than the m2 mass. Then we have concluded that the final velocity v1 will be equal to u1, right? Final velocity v1 will be equal to u1 and v2 will be equal to 2u1 minus u2, alright? You may be remembering the derivation part, it is there in our notebook, right? Okay, and now here we told about a subcase. You guys are remembering there was a subcase, alright? There was a subcase. What was the subcase? Yes, target is at rest. Target at rest. Target at rest. So your u2 will be equal to 0. Then we can tell like v1 will remain as u1, v1 will remain as u1, and v2 will be equal to 2 times u1. v2 will be equal to 2 times u1. Okay, that is after the collision, the heavy body will continue with the same velocity and light body will move with double the velocity of the heavy body, right? Yes, okay. So you can note these points, or you have already learned, it is there in your notebook. Okay. Now what about case 2? Case 2. Okay. What is case 2? Yes, the case 2 is m2 very greater than m1. Alright. So in this case, we obtained our v1 is equal to 2u2 minus u1. Okay, v1 is equal to 2u2 minus u1. And what was our v2? Yes, the v2 was equal to u2. Alright. So here also we have a subcase. Here also we have a subcase, that is target at rest. Target at rest, which means the u2 is 0, right? So here the target is the heavy mass. Our target is the heavy mass. Okay. So what is going to happen? Let's see. We can tell our v1 will be equal to minus u1 and v2 will be equal to u2. Alright, v2 will be equal to u2, which means that after the collision, the light body will rebound with the same speed and heavy body will remain at rest. Okay, so here in the subcase, just a minute, heavy body will remain at the rest, right? u2 we put 0. So this u2 we have already mentioned here, u2 is 0 because target is at rest, right? So v2 is equal to 0. v2 equal to 0 means the target will remain at rest, but the lighter one will rebound. Okay. Now, what about the case 3? We'll go to case 3. Case 3. What was the case 3? Yes, two identical masses or two masses, two bodies with same mass are colliding, right? So in this condition, our m1 is equal to m2. We'll commonly take it as m, right? So they are identical bodies. So in this case, our v1 is equal to u2, right? v1 is equal to u2 and v2 is equal to u1. v2 is equal to u1, which means they interchange the velocity, right? They will interchange the velocity after collision. Here also we have learned one subcase. You may be remembering. We learned one subcase. What was it? Yes, target is at rest, right? Target is at rest. So when the target is at rest, we can tell the u2 will be equal to 0. Therefore, we will get v1 is equal to 0. v2 will be equal to u1. What does this means? Yes, after the collision, the first body will come to rest and the target body which was at rest will start to move with the velocity of the first body. Alright? It's nothing but the velocity interchange. That's all. Okay. So first mass will come to rest and second mass move with the velocity of the first mass. Okay. Now we have already learned about inelastic collision, that in inelastic collision the momentum is only conserved and kinetic energy is not conserved. Now in perfectly inelastic collision, how can we write the equation? In inelastic collision, perfectly inelastic collision, we told that the momentum is only conserved, okay, and kinetic energy lost is maximum. The two bodies will stick together after the collision. So how will you write the equation? If the two bodies stick together after collision, then they have a common velocity, right? So we'll write the equation m1 u1 plus m2 u2, that is momentum before collision, is equal to m1 plus m2 times of v, right? So this is the equation that we will be using for perfectly inelastic collision. Okay. Now let's discuss about oblique collision. Okay. Oblique collision. What is oblique collision? Yes, 2D collision, right? Oblique collision. Oblique collision means it is 2D. Okay. In oblique collision, the bodies will not be moving in the same line before or after the collision, right? So let's consider a case, okay, let's consider a case where there is a mass m1 which is moving with a velocity say u1, and we have a target body m2 which is initially at rest, okay, so u2 we can write it as 0, and they collide, okay, they collide. So suppose initially they are in the same line, they collide, and what happened? The m1 mass move with a velocity v1 at an angle theta 1 with the initial direction, and m2 mass move at an angle theta 2 with the initial direction. Okay. As we know that momentum is a vector quantity, we have to resolve it into x-axis as well as y-axis, alright? So this component of velocity we can resolve as v1 cos theta 1 and the y component as v1 sin theta 1, alright? Now for the second mass we can resolve it as v2 cos theta 2, and along y we can resolve it as v2 sin theta 2, right? Now you will apply the momentum conservation along x separately and along y separately, right? So along x we will first do along x. So along x, what is the initial momentum? m1 u1, okay, we don't have to write m2 u2 because u2 is 0. So m1 u1 is equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2, alright? So this is along x. Now what about along y? Along y we can write, along y initially there is no motion, alright? There is only motion along x initially, along y there is no motion initially, but after collision there is motion, okay? So you will write 0 is equal to, now what is the final momentum of the first body along y axis? We can write m1 v1 sin theta 1. How will you write the next one? Yes, it is not plus, minus, it will be minus. Why? Because it is along negative y axis, alright? So you will put minus here, minus m2 v2 sine theta 2. So we can write this as m1 v1 sine theta 1 is equal to m2 v2 sine theta 2. So this is the equation for oblique collision, but it may not be the case always. Okay, I have shown you one case. So according to the question, you have to conserve the momentum along x-axis as well as y-axis separately. Okay, now let's learn about the topic coefficient of restitution. Okay, coefficient of restitution. I know you guys have already learned all these things, but just as a revision, okay, a short time revision, we can utilize it. So coefficient of restitution. Coefficient of restitution. We will represent it as E, right? How do we define it? Yes, velocity of separation by velocity of approach, right? Velocity of separation by velocity of approach. So we'll write the equation as E is equal to V2 minus V1 by U1 minus U2. It's a very important equation. Okay. And now few points that you already learned. What is it? Yes, your E value will be like 0 less than or equal to E less than or equal to 1. Now suppose E value is equal to 1, then what it represents? Yes, it represents elastic collision. It represents elastic collision. Suppose your E value is equal to 0, then it represents perfectly inelastic collision, and 0 less than E less than 1, it represents inelastic collision, right? Now how to find the final velocity for inelastic collision? Final velocity of colliding bodies for inelastic collision. Okay, what is the equation? Yes, the equation is very easy. V1 is equal to m1 minus em2 by m1 plus m2 into u1 plus 1 plus e into m2 u2 by m1 plus m2, right? Similarly, how to write the equation of V2? Yes, the V2 equation is m2 minus e m1 divided by m1 plus m2 into u2 plus 1 plus e into m1 u1 divided by m1 plus m2, right? And how to find the laws of kinetic energy? Okay, it's a important equation. Laws of kinetic energy equation we have studied. Laws of kinetic energy. How to find the lost? Yes, the lost can be found as kinetic energy initial minus kinetic energy final. Okay, now there is an equation for it. Half into m1 m2 by m1 plus m2 into u1 minus u2 the whole square into 1 minus e square, right? So this is the equation corresponding to laws of kinetic energy. So we will be doing the questions. Okay, now about dropping a ball from a height, that concept we will discuss in the next video, as well as we will be doing the questions, so you can watch the second part.